In this video, we're going to show you how to simulate a simple differential drive robot for ROS. Whereas the Turtlebot tutorial provides you a finished model to play with, you don't get a good sense of how to modify it. So we're going to try to build one from scratch. There aren't many complete up-to-date tutorials that worked on my system with the following software and hardware. So hopefully this will help you get up to speed more quickly than it did for me. The tutorials I used to learn from are these ones, and they're very, very helpful. So in the first part of this video, I'm going to show you a completed differential drive model included in the repo here. In the second part, I'm going to go piece by piece and show you how to assemble the product yourself so you can better understand how ROS and Gazebo fit together. So first, go to your home directory. Clone the image, and basically you'll have a directory structure that looks like the following. In the source folder, there's going to be three main packages: control, description, and gazebo. Next, we're going to want to build it with catkin, either catkin build or catkin make. Notice that catkin will automatically find the packages that are in the workspace and build them. So now that it's built, we can launch Gazebo Simulator first using our ROS launch. Usually ROS launch, if we press tab, will automatically find the packages that match. In this case, it's not finding it because it doesn't know to look in this directory for ROS packages. So there's a simple script to help you do this. And that way you don't run this script ever again. So now we can try ROS launch. And if you notice, it'll find the three packages. And we're going to start with the Gazebo package. It also automatically finds the corresponding launch file. So now we have our simulated differential drive robot. It's composed of a rectangular base, two cylindrical wheels, and a spherical caster. You can view the wireframe to kind of see through these objects and see the different pieces. You can also view the joints to see how the wheels are connected to the chassis. So now we want to make the robot move, and we can do this by publishing a particular type of message to command velocity. In particular, we're looking at the robot's waiting for geometry twist messages, and if we press tab, ROS automatically tells us the format that it's looking for. So we're going to make the robot go in roughly a basic circle. You can see that the robot reacts accordingly and moves around in our simulated environment. We don't want to just work in Gazebo. We want to take advantage of the features that ROS has available. And this is really best visualized in this diagram here, where the idea is you can have any sort of simulation, like the Gazebo simulator, and you can have hardware as well, and as long as they communicate through this common interface, then any ROS packages that we build should be able to apply to both simulation and hardware. This is great for developing algorithms for ROS in simulation and testing them out robustly before moving on to hardware, where the wear and tear might be a bigger issue. So it's pretty nice to have the setup where you have both simulation and hardware capable of running the same exact ROS code. So to do this, we're going to want to launch RViz. And so in our description package, there is a RViz launch file. Now if you'll notice, nothing actually shows up in RViz. And this is for two reasons. First of all, we need to fix our frame to the geometry frame, And you can see this works because the global status becomes OK. And we need to add our robot model. And now you can see that we have both the simulated robot and the robot moving in RViz. And so at this point, you can basically do whatever you want to this model. So for the second part of this video, I'm going to show you how we built this differential drive model. Let's begin by downloading a zip file with the current base branch so that I don't have to spend a lot of time typing. There we go. And I'll delete this directory. So now we're going to go ahead and create our workspace using these commands. So now you can see we have an empty directory with no packages. We're going to create our first package, the Gazebo package. And this will happen in the source folder. Notice that once you create this, you have two files that are needed for ROS to identify this package. Now I'm going to go ahead and copy over from the repo the worlds and launch folder. The launch file basically sets some parameters and launches an empty world file. If I comment out the 2 lines here, we'll also see that we're loading in a world file. So let's see what this world file looks like. It is basically a ground plane, the light source. For convenience, I've added a couple shell scripts. Basically just kills off any remaining ROS or Gazebo processes. And then of course just launches our package launch file. So now you'll see this is an empty world in simulation. Of course, we can edit our world file to have something more interesting, like the Willow Garage model that's included. You can see that we now have a more complex model that we can then later on insert our robot into and see how it performs. To actually add our robot, we need to create our second package, the description package. I'm going to copy over just the URDF file, folder. The main file is the Zacro file, which specifies the URDF specification of this robot model. You'll see that this file includes the other 3 files, Gazebo, materials, and macros. Basically, you have several pieces of our model. You have the main chassis, represented by a box. You have casters, represented as a sphere, and left and right wheels, as well as the joints to make sure that the wheels are attached to the chassis like so. Now first, let's comment out the Gazebo file. If we look in the Gazebo file, we'll notice that it adds this plugin that will actually drive the robot around. So right now, we're only specifying what the robot should look like. If we go back to the launch file and insert the robot model, we should then be able to load We'll load the simulator again and notice that there is, once again, our robot model. Now notice that it actually has no colors this time, because these colors are specified within the Gazebo file, in which we specified that it should be orange. But since we commented it out, that's not going to happen. In addition, if we try to publish commands to it, notice that if I hit tab, there's no robot listening to the command velocity message, therefore we can't. Even if you try and send messages to the robot, it's not going to respond. Okay. Now, so by then uncommenting this Gazebo file, which will then include this Gazebo plugin, we can relaunch our model, and the robot is not only orange, but it will begin to move once we give it commands. To load RViz, we're going to copy over the launch folder to the description package. This file specifies the robot description, which takes in the model that we specified, the robot joints and links. We're also publishing the joints, the state of the joints, as well as the robot state. And then we're launching RViz. If we fail to include the robot state publisher, we can of course still launch Gazebo. The robot can of course move. But the robot state is incorrectly reflected in RViz, where the wheels are no longer attached to the body. And we'll notice two weird things about this. First, we can look at the ROS nodes, where the Gazebo simulator is directly publishing to the transform tree, but nothing about the joints are being used. We can also view the transform tree and see that the odometry frame is directly connected to the chassis frame, and that's it. By fixing this, the robot now knows how the robot's wheels are attached to the main body. You'll notice now that the odometry frame is connected to the chassis, which is also then connected to the left and right wheels. If you look at the ROS nodes, we now notice that the robot state is incorporating the joint states to influence and update the transform tree as well. Hopefully this is enough to get you started with Gazebo simulations in ROS.